In the last video we defined the determinant of an n by n matrix, and in particular there was a formula for it which summarized the slightly wordier explanation I gave, which is the determinant of a matrix A is the sum over a set of n factorial choices of permutation of the sign of the permutation, which is either plus or minus 1, times a product of matrix entries, one from each row, so A1, and then sigma 1 picks which column your entry is in, A2, sigma 2, all the way up to AN, sigma n. So remember, this is a product of matrix elements, one from each row, satisfying the property that no two are in the same column, so that the sigma 1, sigma 2 up to sigma n is a permutation of 1 up to n. And you sum over all possible permutations. Okay, and the sign was plus or minus 1 depending on whether you needed an odd or an even number of transpositions to get from the permutation back to the original ordering 1 up to n. In this video we're going to prove some properties of the determinant which will prove very useful for computing it. So first of all, lemma, if two rows coincide, so they're the same numbers on two of the rows, then the determinant is 0. So for example, 1, 1, 0, 1, 1, 0, 2, 4, 5 has determinant 0 because the top row and the second row coincide. So the proof, we're going to use this formula and some index notation. So let's see what it means for two rows to coincide in index notation. Well, let's say if row I and row j coincide, then that's saying a I k for any k is equal to a j k. Right, in row I, the kth entry agrees with the kth entry in row j. When this happens, the terms in this sum up here for the determinant come in pairs. And what are those pairs? Well, each term is something like sine sigma a1 something up to a I sigma I up to a j sigma j, etc. So I'm just going to write dots for the factors of a that I'm not using, I'm not interested in. So each term looks like this, and we have this identity that aik equals ajk. So this factor here, this product here is equal to sine sigma dot dot dot, nothing changes, then a j sigma I dot 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 a I sigma j dot dot dot, using this condition that the rows coincide. But these factors are just numbers, so we can commute everything past each other, and we get a I sigma j dot 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 a j sigma I dot dot dot, and now we see this is another term in our sum, but instead of corresponding to sigma, this is sine sigma dot 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 a I sigma prime I dot 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 a j sigma prime j dot dot dot, where sigma j is the permutation which first, or maybe I should say, it sends I to sigma j, it sends j to sigma I, and it sends anything else to sigma of, so it sends k to sigma k for all k not equal to I or j. Okay, so the dot dot dots are unaffected. Sigma and sigma prime agree for those factors, but for these two, sigma prime I is sigma j and sigma prime j is sigma I. Okay, so this equality is true by definition of sigma prime. So how many transpositions does it take to do sigma prime? Well, first you do sigma, and that takes a certain number of transpositions, and then you do one further transposition and you swap sigma I and sigma j. So sigma prime is sigma followed by the transposition sigma I switches with sigma j. So the sign of sigma prime is, well, it's the opposite of the sign of sigma because it's one extra transposition. So if sigma was even, then this sigma prime will be odd and vice versa. So this is minus sine sigma. So overall, what we see is that for every term like this, there's an opposite cancelling term where we replace sigma with sigma prime. And the sign changes because of this equality here. So every term has the same term in the determinant coming with an opposite sign, so in total the determinant is 0 because all these pairs cancel. So if two rows coincide, the determinant is 0. So this allows us to prove the first really crucial lemma, the really crucial property of how the determinant changes under row operations. So if A prime is obtained from A by the row operation Ri goes to Ri plus lambda Rj, then det A prime equals det A. So this is incredibly useful because we can do any of these row operations here, these type 1 row operations, without changing the determinant. So if we can row reduce our matrix using just these type 1 operations to something very, very simple, then maybe we can just read off the determinant. That will be the trick. So proof, well, det A prime is sum sine sigma of what? Well, there's a product of terms. A prime 1 sigma 1 dot dot dot, and then I'm going to keep track of the ith row here because that's going to be the important one. This is A prime I sigma I all the way up to A prime n sigma n. Okay, we can say what these entries are. So the first row, second row, etc. are all the same as the rows of A except the ith row, which is given by Ri plus lambda Rj. So this is sum of sine sigma A1 sigma 1 dot dot dot, and then AI sigma I gets replaced with AI sigma I plus lambda AJ sigma I. Dot 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 up to A n sigma n. Okay, so let's multiply out the brackets here. We get two things. First of all is actually just the determinant of A. And the second term is going to be lambda times something else. So this is the determinant of another matrix here, this guy. This is the determinant of the matrix obtained from A by replacing the ith row with the jth row. So this is the matrix whose first row is the first row of A, the second row is the second row of A. The ith row is now the jth row. Oops, that's supposed to be an R. The jth row is already the jth row, and then all the way down. And two of those rows are now the same, Rj and Rj. Right, so the ith row and the jth row of this matrix are equal, so by the previous lemma this is 0, this whole term here. This term here is just by definition the determinant of A. So overall this is det A. Okay, so performing type 1 row operations like this, adding on a multiple of row j to row I, doesn't change the determinant. So the reason this is so important is that we can put any matrix into echelon form using these type 1 row operations, and when you're in echelon form your determinant is just the product of diagonal entries. So example, put A into echelon form. Right, because the leading entries are always moving to the right, you always have something that has zeros below the diagonal. So the diagonal is some like A, B, C, etc. And below the diagonal we have zeros. It could be that some of the diagonal entries are also 0, but below the diagonal is all zeros. And now, as we've said before, the determinant of something that's upper triangular like this, so we don't know what's up here, it could be anything. But the determinant of something upper triangular like this is just the product of the diagonal entries. Because you have to pick this bottom right thing from the bottom row, and then you have to pick the next thing up on the left from the next row up, and you end up being forced to pick all the diagonal entries. So put A into echelon form, then det A is the same as, I should say put A into echelon form using type 1 row operations. Then det A is unchanged, so it's equal to the determinant of the echelon form, which is just the product of diagonal entries. If you use other row operations, your determinant may change, but it changes in a relatively benign way. So lemma, if A prime is obtained from A by switching two rows. Say Ri goes to Rj and vice versa. Then det A prime equals minus det A. So you're allowed to switch rows as long as you keep track of the sign. So that every time you switch rows, you change the sign of the determinant. And again, this is just because every term in det A is something like sine sigma A. Well, let's say A prime. Let's det A prime. A prime 1 sigma 1 up to A prime I sigma I up to A prime j sigma j up to A prime n sigma n. And right, if we just switch two rows, all these other entries are the same, so we can get rid of the primes except on I and j. And this A prime I sigma I is the same as A j sigma I, and A prime j sigma j is A I sigma j. So again, this is equal to sine sigma A1 sigma prime 1 A I sigma prime I A j sigma prime j A n sigma prime n, where sigma prime is sigma followed by the transposition that sends sigma I to sigma j, and vice versa. And now this is just minus the sign of sigma prime. Because there's one extra transposition. So the signs change. So for every term in the determinant of A prime, there's a corresponding term in the determinant of A which occurs with the opposite sign. So overall, the sums are just they differ by a minus sign. Finally, I'll just tell you how the determinant changes if A prime is obtained from A by the row operation Ri goes to lambda Ri. Well, the determinant just rescales by lambda, and you can prove this using index notation in exactly the same way as the other two. It's actually even easier. If you just write out the definition of det in index notation, the factor of lambda will just pull out to the front. So if you use these type 2 row operations, the determinant will change by whatever lambda you're using to multiply by. Okay, in the next video we're going to use these lemmas to calculate the determinant in a bunch of examples.